Good morning, everyone. Today we're going to look at one new topic called the Laplace transform. Okay, Laplace transform is important to solve ordinary differential equation or differential equation. So we want to look at the basic property of Laplace transform. The idea is we want to transform a function to another function. Okay, the definition of Laplace transform is given as integrate from 0 to infinity exponent negative st ft dt. This is called the Laplace transform. Definition. Okay, you have to integrate. You have to integrate from 0 to infinity. 0 to infinity to transform the function. So this is a given function that you want to transform. Okay, the interval is bounded from 0 to infinity. Okay, so this is what you call infinite integral. Okay, so where you gotta use a limit. Okay, for instance, the solution for, let's say, ft. So when you write this transform, we will say the Laplace transform of ft is given as this. Okay, so the ft will transform to a big F S. Okay, so if you look at this, let's say we want to find the Laplace transform. Let's say ft is 1. So if ft is 1, okay, we can see that the integral, where I will write Laplace of 1 is given an integral from 0 to infinity e negative st dt, because ft is 1 here. Okay, so to solve this infinite integral, what you do, you take the limit, you change from, let's say, b approach infinity 0 to b exponent negative st dt. Okay, now you can apply the limit, okay, because the derivative of this respect to t is given as exponent. Integrate exponent will give you exponent negative st. Now taking the derivative of this one and write it on the bottom. Okay, there you go, 0 to b, and don't forget your limit. Okay, so we write it as limit b approach infinity. So solving for this, we know that. So before we apply the limit b approach infinity, what we do, we solve this definite integral by putting b at t. We have exponent negative sb over negative s minus exponent negative 0 over negative s. Okay, when t is b and t is 0. Okay, we are substituting the value to t, not s, because you are integrating respect to dt. Okay, then what happened here, we see that when b approach infinity, exponent negative infinity approaches 0. Okay, and then you have negative, negative, positive. E to the power 0 is 1. So you have 1 over s. So if we say that if s greater than 0, it works fine, but if s less than 0 is diverges. Okay, so when the integral converges, the result is a function of s. Okay, the other notation of limit that we can consider is this one. Okay, let's say for instance I have the Laplace of ft. This gives me big F, and then the Laplace of gt, it gives you big GS, and then the Laplace of yt, it gives you the big YS. So what can you see in common? You can see that t will transform to s. T transform to a little s, and the small case, the lower case, transform to a uppercase. The lowercase is transformed to the uppercase in all cases when Laplace is used. See that? Okay, so you can see this transformation, the notation. Okay, so what we know now, we know to apply the Laplace transform, you need to solve the integral. And we have seen one example, the Laplace transform of 1 gives you 1 over s. Okay, let's look at a few more examples. What is the Laplace transform of t? Okay, find the Laplace transform of t. Okay, so what we want to take note here, our ft now is t. Okay, this is our ft here. Okay, so by the Laplace definition, the Laplace transform of t is given as this definition, which is integral from 0 to infinity exponent negative st ft dt. So we know that ft is t, so I'm going to change it to exponent negative st t dt. Now you have to do integration by part. Okay, integration by part to solve this. So the integration by part, let's write it here in a different color. Let's say u equals to t and dv equals to exponent negative st dt. So differentiate du dt is 1, integrate this one, will gives you exponent negative st over s. Now the integration by part, by integration by parts, what do we know? We know that the definition is uv minus integrate v du. Okay, so let's put it into this notation. U is t, v is exponent negative st over negative s. Okay, and then we wanna integrate this from 0 to infinity, and then we have this minus 0 to infinity v, which is this thing here, exponent negative st over negative s. Now du is dt. Okay, this is easier now to solve. Okay, I'm not gonna apply the limit first. Okay, just put it here like that. So t exponent negative st over negative s. This is from 0 to infinity. Okay, we gotta transform this to limit. Now this one here, we know that this is limit b approach infinity. 0 to b exponent negative st over negative s dt. Okay, integrate first. So what we have here, when I integrate minus exponent negative st, so I can take out negative 1 over s, that will make this positive. I have 1 over s. Okay, now integrate this thing again, it gives you negative s, 0 to b. Okay, so now we have, okay, so now we can simplify this by taking the limit. Okay, this is from 0 to infinity, right? But we have to apply the limit b approach infinity for t exponent negative st over negative s. Negative, bring it to the front, will be negative exponent st over negative s, 0 to b. Okay, so you can actually, if you're a bit confused, you can actually do not apply this limit here. Okay, just leave it in uv, and then at the end you combine them and apply the limit from 0 to b. Okay, but just don't get confused with this notation. Okay, now taking the limit, applying when t is b, so I have b exponent negative s b over negative s minus e negative s b over negative s minus 0, okay, when t is 0, minus e negative 0 over, I'm sure I have bring the negative out, so this is positive. Okay, s. Okay, let's check again. So we have this notation now, and oh, I will even forget this is s squared. 1 over s divided by multiply by 1 over s, so I have s squared here. So don't do mistake like me. And then this negative here, bring it to the front. Okay, so now what we have here, okay, forget about b here, but look at this b. When b approach infinity, this term tends to 0. Exponent negative infinity tends to 0, okay? And then this side here, similarly, when b is infinity, this term also tends to 0. Okay, and then what we have here, positive, negative, e to the power 0 is 1. So we have 1 over s squared. Okay, so this is one example on how to find the Laplace transform. So what do you have here? You have this one. The Laplace transform of t is 1 over s squared, and the Laplace transform of 1 is 1 over s. This is what we have looked at. There are a few more examples we can look at. Let's look at one more example. So let's say we want to evaluate the Laplace transform of exponent negative 3t. Okay, so what we do now, okay, as usual, we use the definition of Laplace transform, where the Laplace transform of exponent t can be written as integral from 0 to infinity exponent negative st ft dt. Okay, now what is ft? ft is exponent, this one. This is my ft, exponent negative 3t. Okay, so now we have integral from 0 to infinity exponent negative st exponent negative 3t integrate from dt. Okay, so what we do here, so you don't have to use integration by part here because you can actually factor it out. So I want to factor it out from 0 to infinity, factoring out negative t. So I want to write s plus 3 t dt. So I'm factoring out t, take out the negative. So when I expand it, I have exponent negative st minus exponent negative 3t, which are the same. Okay, now you can integrate. Okay, integrating here means applying the limit b approach infinity, integrate from 0 to b, exponent negative s plus 3t dt. Okay, so integrating this, okay, we have exponent negative s plus 3. Integrate exponent, give you back exponent, and then you look inside here. The differentiation of this, see, I'm saying differentiation of t is negative s plus 3, right? So you write it on the bottom. So we have negative s plus 3. Okay, so this one now from 0 to b. Okay, depends where you want to write your negative. You can write it in the front or bottom, doesn't matter. Okay, now we're going to apply b first before you take the limit. Okay, so when t is b, we have negative exponent negative s plus 3b over s plus 3. I brought the negative up, and then minus, okay, negative negative. Okay, you have minus here, and then let me just write it here. Okay, and then when t is 0, I have negative s plus 3. This is where my t is 0, s plus 3. Now this is a silly way to write, but it's okay. If you want to avoid mistake, you can actually do this. There's no harm in doing this. The main thing is at the end you simplify. Okay, simplify your operation here. So now we have b. Okay, this will remain the same. Okay, what happened here? Negative negative will give you positive. Now exponent to the power of 0 is 1. So 1 over s plus 3. Okay, so now what we want to do, we want to apply the limit. Now limit is applied to b. So here we don't have to apply limit because there's no b here. So we apply limit when b approach infinity here. This term will approach 0. Okay, so we left with 1 over s plus 3. Okay, and take note that s must be greater than negative 3. You cannot have 0 in your denominator. Okay, so what I mean here, the Laplace transform of exponent negative 3t is given by 1 over s plus 3. So let me just summarize what we have obtained so far. I'm going to use purple this time. Okay, so we have obtained the Laplace of a constant 1 is 1 over s. We have obtained the Laplace of a variable t is 1 over s squared. And we have obtained the Laplace of exponent negative 3t is given by 1 over s plus 3. Okay, so there is a Laplace table that I can summarize this thing. So the Laplace table is very useful where you don't have to evaluate the integral all the time. So the table of Laplace is given as this. So you can actually Google to find out the table of Laplace. So if you're given ft, in here you are given the Laplace of ft. Okay, for instance, Okay, I know that when ft is 1, my Laplace is 1 over s. Okay, and then I know that when this is t, I have 1 over s squared. But how if I have t squared? T to the power 2. So Laplace t to the power n is n factorial over s n plus 1. Okay, so, and then we have exponent 3t here is 1 over s plus 3. So what it means here, if I have anything like exponent 2t, exponent 5t, or exponent at, the Laplace of exponent at is given as 1 over s minus a, provided s is greater than a. And in this case, s must be greater than 0. Similarly for this one. Okay, these are the two things that you have learned. So what this means here, again, you can derive this by taking the integral. Okay, but I don't want to do that. So what it means here, if I have Laplace of t to the power of 3. Okay, based on the table here, I'm looking at this table here, where my n is 3, right? So I have 3 factorial over s 3 plus 1. So the solution will be 3 factorial over s to the power 4. Okay, you can simplify 3 factorial as 6. So 6 over s4. Okay, and then it also means that the Laplace of exponent 5t. So you can use this one here where it's given as 1 over my a is 5, s minus 5. It's much simpler than solving the integral. So you can use the Laplace table. You can modify it according to what the constant here. Okay, let's look at the Laplace of sine 2t. Okay, you want to find this Laplace of sine 2t. So by the definition, we have 0 to infinity exponent negative st ft, which is my sine 2t dt. Okay, so now with this, what we can do here, we can try to solve it in a normal way, but let's change it to limit first. This will be limit b approach infinity, integrate from 0 to b, exponent negative st sine 2t dt. Okay, so you have to use integration by part to solve that. Okay, so where my u equals to sine 2t, dv equal to exponent negative st. So we have du dt equals to 2 cos 2t, and integrate v with dt will give you exponent negative st over negative s. Okay, so the Laplace transform of sine 2t is given by this limit b approach infinity. Now this is the part where you have used integration by part. Okay, integrating from 0 to b. Let me just write it first. Sine 2t dt. Okay, so we want to use integration by part, where you have the integration by part formula given as, okay, so we have uv from 0 to b minus integrate v du, integrate from 0 to b. Okay, so just be careful when you're doing the integration here. So I have limit b approach infinity. Now what is u? Where u is given by sine 2t. This is u. And then v is given by exponent negative st over negative f. Now the limit is from 0 to b. And then we have minus v du. So we have minus integrate from 0 to b. V, which is exponent negative st over negative s, and du is 2 cos 2t dt. Okay, so look at this. Looks like we're going to have another uv formula later on, but let's simplify. So I have limit b approach infinity. This one gives me 1 over sine negative sine 2t exponent negative st. Now I'm going to evaluate from 0 to b. Negative give you positive. Now constant 2 and s, you can take it out. So that will be 2 over s. Integrate 0 to b. Exponent negative st cos 2t dt. Okay, so you have to apply one more time. The integration by part. Okay, so what happened here? Now I can set again, same thing. This is my u. This is my dv by integration by part. Okay, so limit b approach infinity. I have negative 1 over s sine 2t exponent negative st from 0 to b plus 2 over s. Now you have to work with me as I'm doing this because it can get too long and complicated. So we have uv, u is this one, so we have cos 2t, and v, which is integration for dv, okay, where you get exponent negative st over negative s. Okay, again this is from 0 to b, minus v, which is this thing here, exponent negative st over negative f. Now du is the differentiation of cos 2t. That will give you 2. Differentiate cos will give you negative, so this will become positive sine 2t. Okay, so look at this. So let me just recall to you what I've done if you are getting a bit confused. So what I did here, this is my uv minus integrate v du, where my u equals to cos 2t and dv equals to exponent negative st dt. So I just use the integration by part formula and I end up with that. Okay, so what here means here, now I have a big bracket here because the limit is applied for this whole integration here. Okay, so before we do anything, let's simplify. So I have the Laplace of sine 2t, which is equals to, I'm not simplifying there, just copying and see we can simplify the negative and positive first. So sine 2t exponent negative st, this is from 0 to b. Okay, you gotta be careful here. So let's look at this here. So we have s and negative sign. So I just say be careful. Okay, so I have negative 2 over s squared cos 2t exponent negative st. Take out s and s squared and negative. This is from 0 to b. I'm going to write minus here. Minus. Okay, let's look at this one. I have to integrate 0 to b. Take out the s, but this 2 applies for this whole bracket, right? So 2 over s squared. Are you with me? So this is for this thing. This is multiplied with this. So I have 2 over s squared. Exponent negative st. 2 multiplied with 2. Actually, we have 4. 4 sine 2t, and the limit b approach infinity. So this is what we got. Hey, where can this lead to? Okay, where can this lead to? If you look at here, are we going to apply integration by part again? This problem will never solve if you keep integrating by part. But what we can see here, earlier on, this definition we wrote as like this. Laplace of sine 2t is, by the definition, 0 to infinity, exponent negative st, okay, sine 2t, right? Which is equals to this, limit of b approach infinity, negative 1 over s, sine 2t exponent negative st, from 0 to b. The limit applies for this whole thing, so 2 over s squared cos 2t exponent negative st, again the limit from 0 to b, okay, and then minus limit b approach infinity 4 over s squared integral from 0 to b exponent negative st sine 2t. Now what I'm doing here, you can see there's a common term here, exponent st sine 2t with this part here, right? Now this indefinite integral, I can write it as limit b approach infinity 0 to b exponent negative st sine 2t, which is equals to limit b approach infinity negative 1 over s sine 2t exponent negative st from 0 to b minus 2 over s squared cos 2t exponent st from 0 to b. So now we have minus limit b approach infinity 4 over s squared. Now this part here, integrate 0 to b exponent negative st sine 2t. Okay, so we can see the common term here. Okay, if you look properly, there's a common term involving this one here, this and this. You see that? So we can factor it out. So I want to bring this whole thing on the other side. That gives me limit b approach infinity, integrate from 0 to b exponent negative st sine 2t dt. Okay, I always forgot to write dt. This one negative, bring it there, will be plus 4 over s squared limit b approach infinity, this part here now, integrate from 0 to b exponent negative st sine 2t dt. Okay, there's a long work here, so don't forget equals to, I'm going to write it equals to, maybe here, the upper part, which is limit b approach infinity negative 1 over s sine 2t exponent negative st from 0 to b, and then minus limit b approach infinity. So this part here, first is this one, the second one is this part here, 2 over s squared cos 2t exponent negative st from 0 to b. Look at here, this is a long, but you can simplify this. Factoring this one out, I have 1 plus 4 over s squared, okay, limit b approach infinity, integrate from 0 to b exponent negative st sine 2t dt, okay, which is equals to this whole thing here. So you can apply the limit now. Limit when b approach infinity, okay, but before that, put the integral b first when you see t. So I have limit b approach infinity, negative 1 over s sine 2b exponent negative sb minus will be positive exponent e to the power 0, but sine 0 is 0. Okay, that's the first part. And then we have the second part, which is this one, minus limit b approach infinity 2 over s squared. Now when t is b, I have cos 2b exponent negative sb, again minus, so my minus in the front, so I'll just put minus here, 2 over s squared cos 2 times 0 exponent negative 0. Okay, so we have what we have here. Okay, it's not that complicated actually. So this is what Laplace, this is what we can write as the Laplace of sine 2t. Okay, so I have 1 plus 4 over s squared Laplace of sine 2t equals to, okay, now this term here, when b approach infinity, this part approach 0. When exponent b approach infinity, this part approach 0, where e to the power of 0 is 1. And similarly, we have, however, cos bt, cos when b approach infinity, okay, this is also vanishes, okay, and now here, e to the power 0, we have this term here, cos 0 is 1, so I have negative, negative, positive 2 over s squared. Okay, let's simplify this. So where I have, so the final step now, I can just, if you're not too sure how to bring it to the other side, just simplify the denominator in the numerator. So I have s squared plus 4 over s squared, the Laplace of sine 2t, okay, which is equals to 2 over s squared. Now we're almost there. All we gotta do is we gotta bring this part here to the right hand side. So now the solution for Laplace sine 2t is therefore given by 2 over s squared multiplied with s squared over s squared plus 4. Okay, so simplifying this term, we're cancelling out s squared here. There you go, we have Laplace of sine 2t is equals to 2 over s squared plus 4. It's a lot of work, but this is what you have obtained. Okay, so what we can say here, if I have the definition, the Laplace table definition, I can say that the Laplace of sine at is given as a over s squared plus a squared. Okay, now look at here, when a is 2, I have 2 over 2 squared, which is 4. Similarly, the Laplace of sine 4t, you don't have to do that integral again, which is a complicated integral. So what I do, a is now 4. I have 4 over s squared plus 4 squared is 16. You get the idea? Okay, so now I will leave the rest as your homework. Which is the homework? The homework is, okay, find the Laplace transform of this one, Laplace transform of cos 2t. Okay, find the Laplace transform of cos 2t. So this is your homework. Use the same definition that I gave you for the sine t, where take note that you have to integrate 2 times by part.